Hey guys, today we're going to be going over the different factors that cause populations to grow or shrink, and we're also going to do some calculations around that as well. So let's get into it. Okay, so population growth. So we're going to start by calculating population density, which is a really easy calculation. Then we're going to look at the different patterns of dispersion, which is just how populations are arranged, like how the individuals are spread out. Then we're going to look at all the different factors that affect the number of individuals in a population, and we're also going to be able to calculate the changes in those populations. We'll briefly look at the difference between open and closed populations, and then we're going to calculate per capita growth rate. You also need to know the difference between growth rate and per capita growth rate. So population density is just a way that we measure populations. So the symbol for population density is a capital D with a little subscript P. It essentially measures the amount of individuals, which we represent with a capital N, in a population at any time, per the amount of space. And we measure space in either area or volume. Usually area for anything that lives on the land, and then volume for aquatic populations. So the formulas are at the bottom there. Density is equal to the number of individuals divided by the area, or the number of individuals divided by the volume. So let's do a couple quick calculations of that sort of thing. I'm just going to change my camera here. Okay, so the first question says that there are 12 groundhogs living in 10 meters squared. So our density is the number of individuals divided by the area. So it's just going to be 12 divided by 10, which is 1.2 groundhogs per meter squared. For number 2, it says that there are 16 million plankton living in 4 meters cubed. So this time it's the number of individuals divided by the volume. So 16 million divided by 4, which I need my calculator for, is 4 million plankton per meters cubed. And then the next questions asked us to figure out the population size. So we're still going to be using the same formula, but this time we have the density and the area. So it says the population is living in 1,200 meters squared, and the density is 6.2 individuals per meter squared. So I, of course, just multiply by 1,200 to get my population size. So 7,440 individuals would be the answer to 3. And then for the last question, again, it gives us the density is 11,000 mice per meter squared, which is a lot of mice. Again, we're finding the population, or the number of individuals, and it says that they are living in a 45,000 meter squared habitat. So once again, we just multiply by 45,000. Ooh, and we get, well, I'm going to put this into scientific notation. I don't like writing out all those zeros. 4.95 times 10 to the power of 8 is the number of individuals. Okay, so that's like a super straightforward calculation of density. The expected population density varies a lot from species to species. Usually smaller organisms will have higher population density because each individual doesn't need as much space and as much resources. They don't require as much food because they're tinier. Larger species tend to need more space, tend to need more resources, and also can be territorial. Population density can also be really misleading if part of the area or part of the volume that you're measuring of the habitat is unusable. So for example, if you're looking at some sort of terrestrial organism and you just kind of look at the boundaries of its habitat and calculate that area, maybe you don't take into account that there's like a large pond in the middle of that habitat that that terrestrial animal can't live in. And so really that might make the population density seem less than what it is. You should remove that pond or any non-usable part of the habitat when you're determining the density. You also need to know how population is distributed when you're doing density calculations. So that's what we're going to get into next, the distribution or dispersion patterns, which is just, again, the way that the individuals within that population are spread out throughout the habitat. And there's three main patterns that we see: random, clumped, and uniform. And there's kind of examples of what that would look like at the bottom there, but we will go through each one individually. So a random dispersion just means there's no pattern to how the individuals are arranged. You would not be able to predict where an individual is going to be at any given moment. Usually you only see random dispersion patterns in species that don't form groups for survival or for mating. There's probably not going to be very much competition between individuals, whether that be for territory or resources. And the kind of dispersion of resources and environmental conditions will have to be kind of consistent throughout the habitat, or else the individuals would clump around like the better areas. So it all has to be kind of consistent throughout if they're going to be random. This pattern is very rare in the wild, though. Clump dispersion is when individuals in the population are found in little clumps or groups with spaces between them. This usually happens when the habitat is really varied and then certain resources, whether that be food or water or shelter, are only found in specific areas. And then the individuals of the population form clumps around those like high resource areas. In some populations, individuals also clump together for safety in numbers so that they can fight off predators or work together to take down large prey. And we also see this in the formation of harems, where like an alpha male will have like a large group of females around him. Sometimes these clumps can also be based on family units, but it's not always related individuals that clump together. This is the most common dispersion pattern in the wild and in human populations. Think of like the fact that we organize in like towns and cities and stuff like that. And then lastly, we have uniform dispersion, which is when there is kind of an equal amount of spacing between all of the individuals in the habitat. If you have this type of dispersion, you can totally predict where an individual is going to be based on where another individual is. Usually you only see this dispersion pattern in species that are really territorial and therefore like keep a certain radius around themselves clear. So like we see this in like birds of prey, for instance. We also see this in like man-made habitats, like cultivated areas like orchards and stuff like that, or in species that have a super high population density where the individuals are just super tightly crammed together. And so there's just very little space between all of them because they're just so squished together. Okay, the next thing we're going to talk about is population growth, which refers to the rate of change in the number of individuals in a population over time. Population can be positive or negative. If it's positive, that means that you're increasing the number of individuals. If it's negative, the number of individuals is decreasing. And there are 4 factors that affect whether a population is growing and whether that's positive or negative. The first is mortality, which is just how many of the individuals are dying. The second is natality, which is the birth rate or how many individuals are being born. The third is emigration, so how many individuals are coming into the population. And the fourth is emigration, the number of individuals leaving the population. So we can calculate the change in a population size by taking the factors that increase the population, so birth and people coming in, and subtract the things that decrease population size, like death and people leaving. Delta N refers to the change in the number of individuals. Remember, N is the number of individuals, and any time you see that delta sign, that is just a change in. Then we can look at calculating the growth rate for a population by taking the change in the number of individuals and dividing it by the change in time. So this is the formula for growth rate at the bottom here. Growth rate, which is GR, is the change in the number of individuals divided by the change in time. Remember, when we are doing a change in calculation, always do final minus initial. We will come back to that, by the way. Another thing I want to talk about is the difference between open and closed populations. So open populations are populations where there is emigration and immigration. People can come and go. And that is true for most wild populations. A closed population is one where there's no leaving or entering, so there's no immigration or emigration. In closed populations, the only thing that will affect your change in population size is birth and death. This is fairly rare to have a closed population, but on really like remote, isolated islands and stuff like that, you might see it. Okay, so we talked about what growth rate is, which is the change in the number of individuals divided by the change in time. But per capita growth rate is actually more useful most of the time. So per capita growth rate is the change in the number of individuals divided by the number of individuals you start off with. We can express this as a decimal or multiply it by 100 to turn it into a percent. And this is the formula at the bottom here. So per capita growth rate is CGR, capita growth rate. And it is the change in the number of individuals, which is our delta N, divided by the number of individuals. And that N is referring to the number of individuals that you have initially, that you start with. The reason that this is useful is because growth rate is only telling you how many individuals you've lost or gained, whereas per capita growth rate shows you the amount of growth relative to the population size. So for instance, it might say that a population grew by 40% or doubled in size or something. The reason that this is important is because if you lose 50 individuals a year and your initial population is 4,000 individuals, then 50 individuals a year isn't that big of a change. But if your initial population was only 120 individuals, that's a big change. So if you're only looking at the number of individuals you've lost or gained, you can't actually tell if that's important without knowing if it's a large population. Large populations should have larger growth rates, and smaller populations should have smaller growth rates. But without knowing the population size, we can't tell if the growth rate is a big deal or not. That's where the per capita growth rate comes into. It tells us, is this amount of change in individuals a big deal or not? So let's go through this example here. It says there's a population of snails that was estimated at 3,800 individuals in April of 2015. In April 2017, the population was estimated at 2,700 individuals. Determine the growth rate and the per capita growth rate. So the growth rate and per capita growth rate both start by finding your delta N, your change in the number of individuals. And we always start by doing final minus initial, so 2,700 minus 3,800, which gives us negative 1,100, which is why we have this negative 1,100 here and this negative 1,100 here. Both of those are our delta N's. And then for the growth rate, we take that delta N and we divide it by our delta T. And in this case, 2 years have gone by, so that's our change in time. And so a negative 1,100 divided by 2 is negative 550, meaning that the snail population decreased by 550 snails per year, or it lost 550 snails per year. The per capita growth rate takes that delta N, our negative 1,100, and divides it by the initial population, which is the 3,800. And that gives us negative 0.29, which is negative 29%. So that tells us that the snail population decreased by 29%. So let's go through these practice questions. I would recommend you trying them all on your own based on kind of following this example here, and then come back and check your answers. Okay, so for the first question, it told us that we started off with 560 individuals, and then it says 180 died, so we're going to subtract the ones that died. We'll add the 260 that were born, subtract the 15 that left, and add the 4 that came in. And that gives us a change in population of 629. So for our growth rate, we can take the 629 and divide it by the 18 months that went by and get 34.94 repeating individuals per month. Or we could do it in years instead and take the 269 and divide it by the 1.5 years and get 419.3 individuals per year. And then for the per capita growth rate, we again take our delta N, which is 629, divided by the initial population of 560, and we get a per capita growth rate of 1.12%. Okay, for the second question, it gives us the amount that the population increased by, the 28%. So that is our per capita growth rate. So I know that I'm going to be using my per capita growth rate formula. Anytime we have a percentage, we turn it into a decimal to use it. So we'll plug in 0.28 as our per capita growth rate. And then it tells us that our population in 2010 was 1,300. So that is our initial population. And then we're going to find our change in population, our delta N. And I do that just by multiplying by 1,300. And that gives me 325 is my delta N. Now remember, delta N is your final minus initial as far as the population goes. We know that the initial population was 1,300, so I can isolate my final population by just adding 1,300 to the 325, and you should get 1,625. Now, many of you won't actually use this formula to do this part of the problem. Many of you will just automatically know that you can add the 1,300 to the amount that it's changed by. But yeah, this is the actual formula for it, but either way is fine. Okay, and then for the last question, we start by finding our change in the number of individuals. So it was just measured at 48 individuals. 3 years ago, it was 125. So 125 is our initial. Right now is our 48. So when we subtract those, we get negative 77. For our growth rate, we do negative 77 divided by the 3 years and get negative 25.6 individuals per year. So this population is losing about 26 individuals a year. For the per capita growth rate, we take the negative 77 and divide it by the initial population of 125, and we get negative 0.616, which is negative 61.6%, which means this population is decreasing by about 62%. Okay, that's it for today. And like I said, I think this is the last calculation that you're going to have to do for Bio 30, so enjoy it.